to the chapter number not 5, finish 5, go to chapter number 6. And on chapter number 6, we will talk about field effect transistor or FIT transistor. FIT transistor. Okay. For FIT transistor is another kind of a transistor. Okay, let's open this one and let's talk today about this one. For a transistor, mainly we have two kinds of transistors. Just with the pin. Okay, this one. Okay. Sometimes it's hard to work. Doesn't work the pin today. Okay, for a transistor this times. Just a minute. From Kasper Sky. For transistors, we have mainly two kinds of family. First one it's called BGT, second one called FIT. So we have BGT and FIT. For BGT, we have also two kinds of family, NPN or PNP. Now, for FIT also we have mainly two families. First one called GFIT, and for GFIT we have something called N-channel and B-channel, and here we have something called MOSFET. In MOSFET also we have two families. We have something called depletion, and we have another one called enhancement. For depletion also we have N-channel, B-channel. For enhancement we have N-channel, we have B-channel. So this is if you want, this is kind of families for transistors. So before we studied this one, we studied BGT as first of all physical, then said DC, then AC/DC analysis, then AC analysis. Same thing today. Today we'll start with this one, GFIT. And next week, inshallah, we'll start with MOSFET. Today, this week and next week, we'll start physical. Then we'll go to the DC analysis. Then we'll go to AC analysis like BGT. So today, our lecture about physical component and how this GFIT works. How this GFIT works. Okay, now let's start our lecture from our book and talk about this one. BGT this is important for exam, is a current controller device. GFET is a voltage controller device. What that mean? See this. Current controlled and voltage controlled. If you remember, this is my transistor. I have IB, I have IC. This is ground. So usually IC equal beta IB. That's mean if I change this, this will change. That means IB controls IC, or IC is controlled by IB. Correct. This is called current controller. In another side or another part, we have this one. In FIT, we have something very, very important. What is this? Is input, output, in, out. For GFIT, the main characteristic for GFIT, that means Zn equal infinity. That means In equal infinity. Hojam, here we have IB. Yeah, here we have IB. But take care, Arkadashtar, take with me, excuse me. Bring coffee with you. Here we have VBE. VBE. This VBE is 0.7 volt. Here I don't have I here is 0. So how we can control the output? I will change this VGS. So VBE here for this one is 0.7. Today, inshallah, we'll see that this is called gate, source, drain. Today we'll see this one. So VGS here is not 0 or not constant number like 0.7. So this VGS is variable. Here IB is variable. So different between so the difference between FIT and BGT, that IB is changeable, VBE is constant 0.7. In another side in FIT, IN or IG here, let's use IG, is 0 because Zn is infinity. Why? I will tell you now. VGS is variable. So this is the main difference. This is the first difference. The first difference between this and this, that's mean IB is or BGT is current controller, FIT is voltage controller. Clear or repeat? Because I'm walking slowly because we had this new topic. Everyone, is it clear? Yeah, no. This is the first thing. Check it. So just to check if it's recording or not. Oh, yes, recording. Another thing. In another word, the current IC is direct function of IB. I told you this one. Just there on. Okay. See another thing here. VGS applied to input select as shown in the figure. As I told you, in each case, the current of the output is controlled by parameter of input is current level or other applied voltage. Okay. For BGT, just as there are NBN and PN bipolar transistor. Here we have, as I told, N channel, P channel field. Pi or prefix pi indicate that the conduction level is to charge. Okay. Where is this? Give me this. Give me this. I will write here. Where's the pin? This is the pin. For BGT and FIT. First thing, BGT is current controller. FIT is voltage control controller controller. الله يهديك. R. This first. Second thing, in BGT it's pi. That means we have two current. If you remember, for those two current, we have majority and we have minority. Here we have one. So first or second comparison, that means in BGT I have two currents, majority and minority. For that reason we say pi. Here we have one current, just. Third thing, let's read our book, and from our book we can discuss about this one. Here we for the term field effect in the name deserve some explanation. We are familiar with ability, the magnitude. Okay, this is not important. One of the most important characteristics is high input impedance. Okay, where is this here? For this one, 3, fit is I. Input is 0, Z. Input is high. Here we don't have like this. We have IB. We have number. Micro ampere. And Zn usually equal in kilo ohm. So this is the third thing. So here you can write high level of input impedance. Finished? Not yet. Fourth. Let's continue and see. Typically, the voltage gain AC for BGT amplifier are greater deal with than FIT. Voltage gain for BGT bigger than FIT. Okay, return back to this. AV bigger than AV here. AV, it's right. BGT is bigger than AV for FIT. Okay. Others, write this after that. I take, yeah, after that, I will clear this one. Okay, Control A, delete. Continue. Overbook. FIT are most temperature stable than BGT. Return back. Okay, sorry. BGT, BGT, and FIT. FIT is more stable of temperature comparing with BGT. Now, making them practically useful in integrated IC. Okay, so this is IC contains of IC, that's me here, I see here, integrated circuit, like this. Example, we have input, we have output, contains of FIT. Again, now we are making comparison. Last thing, typically AC voltage for BGT are greater than FIT. FIT are more temperature stable and FIT are smaller than BGT. Also here. FIT is smaller than BGT. But last thing, FIT is expensive than BGT, and here BGT BGT is less sensitive for electrostatic charge. So I guess this is the important thing here now. Now we made comparison between BGT and FIT. Let's talk about this now and make revision for this. BGT is cheaper, less sensitive, greater amplifier, but big size. FIT is smaller, expensive, and more temperature stable. So if you are working with normal circuit, you don't care about the size, small or big. So here you prefer to use BGT and it's sensitive for electrostatic. If you prefer to work with size is very important, precious for you. And you need to, for example, make very controller. So here you prefer to use FIT. So actually, this is based on design of you. Normally, I prefer BGT because BGT is cheaper and is sensitive for electrostatic. That means for if you touch the pin, that means maybe you will destroy the FIT. Otherwise, in BGT, not like this. So this is the main comparison between them. Again, in BGT, you can control output current based on input current, whereas the input is constant 0.7 VBE. In FIT, otherwise is no. Input impedance is very high. Very high input impedance, that means we can make separately or isolator for input from this stage this stage from output of previous stage. And this is also very important for controlling, shall we see now today, about not today, after 2 weeks, about DC current. For BGT we will control IC beta IB. Here we have another thing. What is this thing today? We talk about this how we can control output current based on input voltage. And what is the formula for this one? Any question for this? Clear? Is it clear for you? Yeah. After this lecture, excuse me, take photo for this and write in your notes. Okay, let's cancel this and delete. Let's go for our book again. I told you about the family of for this one, and this is the first BGT. It was in 1955, developed by Dr. Ian Morris Ross, and another one called DC Joint. Those developed this transistor. Now, first transistor called GFET. GFET. G, that means junction. Let's see this. It's a transistor. Junction. In this junction, we have like this design. Junction, by meaning, junction, if you don't know the meaning, is connection or cross or section. What is this cross? See the design of this transistor, excuse me, sirs. I have, first of all, bring in. So this is in. On the sides, I will bring or I will make doping for P. And I will connect. Here we have this is P. On each side, we have here iron. N and B are semiconductor. This is conductor. And here conductor to connect. And I will connect this with this together. This is called GOR gate. And here we have for up, I will use like your book. Here we have also iron or copper. This is called drain. I have here smaller one called S or source. So we have drain D, source G. If I compare with BGT, this is, give me this is called here base emitter collector. And exactly the same job. B like a G, D like a C, it's like a E. So it's like no. Okay, so this is the building of this one. Okay, now there in this case, as there is no any power. This area from drain to source called here called channel. This area. So this is called channel. Okay, so how will this work, or how does this one work? See here, between P and N, if there is no power, we have this area. Hojam, what is this area? This is the depletion region. If you remember diode, this is diode. If you remember, between P and N, usually we have depletion region. This for depletion region, if you remember, for forward, it's PN, depletion region is small for forward, and depletion region is wide for reverse. I guess we know this. So, excuse me, your eyes about this. Here, 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 here. This is the key word for this transistor. How I will tell you. So again, this transistor consists of just N and B. So this one called in channel. This is because this channel, so called in channel. This is called this one here. Stop working the pen. Called in channel. Stop working. This is online. Okay. This is here called in channel. So now in opposite case, if I have B, we can say it is P channel. So this is in channel. B channel, I want to change. Here we have for B channel, I have here P, I have N, so we can say this is P channel. Just to change N with B, B with N. Is it clear with you? Is it clear? Is it clear? How is this one work? You can imagine channel like a water. So in this water came from source to drain, and gate can control it. It's not like BGT. Here we have a current goes from source to drain, and gate is control it. So again, in GFET or junction field effect transistor, we have a current goes from source to drain, and gate will control this. Gate will control this. How will you control this? Now, today we'll start and talk about this one in details. Okay. Okay. I prefer to take 5 minutes break. Then we return back to this one, explain in detail. Don't go away. Now it's 9:06. 9:10 we'll start again, a little bit break. We will again take about this one. So don't go away. Have a nice day. Yes, again, let's start our lecture again. Yes, where is this? Can you see the screen? Excuse me. Can you see the screen? Jalal, Ahmed. Yeah. Now let's start. Thank you so much. First thing about VGS equals 0, VDS sums. Thank you so much. See this case. I will draw this one. Here in this graph, and this is very important, the graph. Yeah. Here we have been stopped and need time to work. I don't know why. Okay, let's see this. I hope to work. Today I have problem with the pen. Okay. Well, now see this. I don't have any power here. I have source, the ground, drain to the battery. 5 volt, for example. Or in our example here, let's use 2 volt. Okay. What will happen here? If I draw again this area, see this area. Here I have 0 volt. Here I have 2 volt. If I see this, I can see here you have 2 volt. Here you have 0 volt. In this channel, you can imagine channel, this is channel, like a resistance. So you have R1, R2, R3, R4. Here I have 2 volt, here I have 0. So we have voltage drop here, for example, I have here 1.5, I have here 1, here I have 0.5, I have 0, and I have 2. Why is this? Yeah, with me, excuse me. Because here I have 0 volt. So I have 0. Here I have 2. This is positive and negative. This is reverse or forward? Ahmed, Jalal. Positive within, reverse or forward? I have this diode. This is PN. N with positive, B with negative, negative, positive. See, positive with negative, forward or reverse. What do you say? Thank you so much, Ahmed. Reverse. That's mean depletion region, narrow or wide? Jalal. For reverse, depletion region is narrow. Thank you. So see here I have 2. So at this point, depletion region is bigger than or narrower than this region. And I use another color, this one. And in this one, is bigger than this one, if this one is bigger than this one. Got the idea? So we can divide or we can consider the channel as a resistor. Four resistors here, for example. So we have voltage drop for each one. Bigger one from a drain, smaller one from source, zero, almost zero, ground. And because we are using, because it is in channel and positive, so it's reverse bias, so it's narrow depletion region. Good. So the depletion region from drain will be will be bigger than source. But not for example immediately we have grade. See here, it was like this. From this side and again from this side. Here also bigger than here, and here also is bigger than here, also bigger than here. So exactly how many depletion regions we have? We have four. The biggest one, the narrowed one from drain, and the smallest one from source. Got the idea? Got the idea? This is now concept. Again, what about VG is zero. We don't have any control. We don't have any control. Again, you can imagine GFIT like a water tap. Water came from drain, or water comes from the drain, and and after that goes to that source. So in this case, it's not like this tab is not same. We have here small, down is small, source is small, source is big, here is smaller, big, bigger, smaller. Got the idea until now? It's clear for you? Is it clear? Okay, okay, good. Now, let's continue with this. Now, see this graph, and this graph is very important. If I draw ID with VDS, that's mean output current with output voltage. So see from this graph, current increase at one point. This is called ohmic region. And after that, if you remember, this is depletion region here, depletion region here. If I increase the current, we find a area, this will be constant, ثابت. This is called saturation level. Again, when VGS is zero, don't forget we don't have any VGS. So here we have to define two things, IDSS and VB. I drain source saturation. IDSS drain source saturation. In IDSSC, current is constant because this area will be constant. And if also I increase the volt, this area will be constant. Again, if VGS equal 0, this area, this region, this volt between, we have, for example, this is VDS. Here we have something called VGS. Here we have another volt called VDG. This volt at this area called VP, be called finish off. What do you mean of finish off? Okay, let's see the finish off. Hojam, well, we don't know in English. Let's see what's the meaning of finish off. If I open any website here and see what the meaning of finish off. Finish off, like hanging. Stop, not like this one. So finish off, that's mean like hanging the current. Hanging the current. So let's read the definition from our book here. Finish off. Finish off. See the finish off? Let's be this photo is not so correctly, by the way. Here it should be space. Like this space. Yes. Because in this area, I have a current called IDSS. So it's not exactly closed. It's not closed. We have a small area or region to pass the current from drain to source. Sorry, from source to drain. This current called IDS, and this is again S saturation. So I from drain to source saturation. I drain source saturation. But Hujam, you told us it came from source to drain. Yes. Yes. Okay. Why we wrote IDSS? Should be ISDS. No. Why is this? You know, for current, we have two kinds of current. We have conventional current and electronic current, correct? Okay. So IDSS, that's I see here. Back. Pen stopped. Today, I have ruined this pen. I don't know. Okay, working. Now, for this current, for positive to negative, this current is electronic current. But we have conventional current. Conventional current from positive to negative. Conventional current from positive to negative. So for that reason, we write IDSS. So conventional current will be from here to here. So we can say IDSS, not ISD. I have wrong today with Ben. Excuse me for this man. Excuse me. Okay. Now let's go for another reason. See this one. So here, if you want to express this with VG 0, VDS is bigger than VB. And here we had definition. IDS is the maximum drain current as the maximum drain current for GFT or for GFET as defined before. Okay, by the condition VGS equals 0 and VDS is bigger than VB or finish off. Now, we studied the first case. So the first case when, first of all, no input voltage, no controlled. Again, what is input voltage? Input voltage is controlled voltage. Input voltage is controlled voltage. See this voltage here, up. If you want, we can return back up and see this. This one. See this. Here we have just from source to drain. No control. So source is bigger, drain is smaller. Again, if we ignore gate, if there is no 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 gate. Okay. If there is no gate, we can find this one. Now, what about if we add control here for this gate? What will happen? Let's see. Again, gate here is B. So I will add negative. Why? Just a minute. Just here we have a key. I wish to work, but I don't know. Allah, today pen isn't working. Okay, I will use my hand. See, here I have B. B is positive. Here is negative. Again, Ahmed, positive with negative, forward or reverse? Reverse. So here I will add more reverse. Off. So here we have double reverse. One from the VDS and one from VGS. So both are reverse. Both are reverse. Both are reverse. Both are here. It's reverse. And also here from this and this are reverse. Excuse me for pen. So here I have double reverse. I have here double reverse. One from gate side, one from drain side. Why? Because I will increase the depletion region more and more. So idea for GFIT is a closed channel. As I told you before, if we have 0, there is no VGS, just we have a channel, we have a current. In this current, this is saturation current, you see? This is saturation current, but still we have a current. Now, if I increase here, I add some voltage, what do I have to do? See my hand, I start to increase this from here and here. So what about this area, the depletion region? This area, come here, will increase more and more until a point. This point, close channel. At this point, we closed channel at this point. So idea for controlling is close channel by adding more reverse voltage and increase depletion region. And see, close start where? From this area, from a drain side. So we start to close from this. At this point exactly, ID here equal 0. And we can say now transistor off. Got or repeat? So idea for exactly, Aryan, see here, we start from reverse bias on VDS. Okay, but still we have a current, not 0. Hujam, I want to close the channel. I will add more and more reverse. Where I can find this one? From here. From here. From here. VGS. So I want to close the channel. I will add VGS here. This is positive, negative. So I will increase channel here, until a while after for example, VGS 1, 2, 3, see this channel will close at this point from drain. So here ID equal 0, and here we can say cut off region. So again, we can say we have omic region, we have cutoff region, we have saturation region, like BGT, but in different way. In BGT, we have another thing. We have either, for example, connection. For BGT, if it's G junction and C junction, off that's mean cut off, off that's mean active, on that's mean saturation. If you remember, I made this table for you. Here we have another. Okay, let's see this for this. Actually, I have simulation for this one, but doesn't work with me. For that reason, I delayed. I hope to find something for this one. Just a minute. I have this SW file. SW file. Here download. Let's check if this is working. Let's check if this is working or not. I hope. Because I have here some file, I can show you this one. So inshallah working, I hope. Macromedia Flash player. Okay. Macro. Let's see if we can find this one. I know this also old one cancelled. Maybe we can find here, I hope. See, I hope inshallah to work. Open, browse. Yes, here. About book. It's textbook. Yeah, this is my laptop. It's textbook. Yes, I got this one. Open. I hope to work. If not, we can say in G bit in channel working. Yes, doesn't work. And doesn't work this one. Anyway, you can find, I want to share, there's a video for this one. I can share with you what I want to see. Share with you. This one. This video. This is this is here. You can see closing channel. See this video.
Hi everyone, myself Muslim Rangwala. Today we'll see the working of junction field effect transistor. Junction field effect transistor has three terminals: gate, drain and source. Gate and source is always connected in reverse bias condition. Here gate to source voltage, that
See
is
the video, excuse me.
VGS, is applied to make it reverse bias. Drain and source is always connected in a way that current flows from drain to source. That is, we can say that electron flows from source to drain. We can see that here the VGS is used to make gate and source reverse bias. So as if we will increase the voltage across VGS, the reverse bias layer, or you can say depletion layer, also increases. As we can see, if we will increase the voltage, depletion layer also increases. So what we will do first, we will keep VGS at 0 and increase the voltage across drain and source. So we can see that if the voltage across drain and source is increases, the flow of an current also increases. If we further increase the voltage across drain and source, current also increases, but the depletion layer also increases.
See this?
This is due
See
to the
this?
positive charge across
See
drain
this?
region. This positive charge,
Again, as I told you before, where's the pen? Here is the pen. Okay.
make the
Excuse me. See the pen here.
voltage across VGS. We will keep VGS at 0 and increase the voltage across drain and source. So we can see that if the voltage across drain and source is increases, the flow of an current also increases. If we further increase the voltage across drain and source, current also increases, but the depletion layer also increases. This is due to the positive charge across drain region. This positive charge make the gate region reverse bias with respect to drain. So because of this, depletion layer increases if we keep at 0 also. This is due to the positive charge across drain. Okay.
See again.
What we can
see here, I want to see after this point here, VB. If I increase volt, this area will be constant. This area will be constant. This is called, and I came from source to drain. This is called I, drain, source saturation. If I increase volt here, this area will be constant. So this is constant. If I draw the graph, increase after that saturation. In your book, they made close. This is wrong. It should be space. Channel doesn't close. We have here I, drain, source, saturation. Which point? This point, VB. After VB, current will be constant. Current will be constant. The depletion region will be constant. Take care about this one. In your book, there is a mistake. See here, after VB, here VB is 3. After VB, IDSS will be constant. So this is called IDSS. Channel doesn't close. We have a current. Still we have a current. Yeah, exactly. Thank you so much. Turkey, see this. We don't control anything for this one. Still this one is zero. Here is zero. There is no control. So again, take care. In your book, there is a mistake. After VB, see this video? After VB, IDSS will be ID will be constant. So for that reason, we said it's ID and source saturation. To see this here, this is VB. See, like my hand. After that, it is constant. It's clear or repeat. This is very important today. Very important today. Should I repeat? Yeah, drain is output. Yeah, Turkey drain is out, like collector. Drain, collector, source, emitter. Gate, base. It's clear? Okay. Now, let's continue.
See that further if we will increase the voltage, current doesn't increases because the channel width remain constant. At which the channel width remain constant, also
See?
the current remain
Pinch
constant.
off is
That voltage is known as pinch off voltage. As we can clearly see that in the graph, pinch off voltage, after that voltage current becomes constant because the channel width become constant. So if now next what we will do, we'll increase the VGS at the starting and we'll keep at a 0 at VDS. So let's say if I will keep VGS at -1 volt, and further if we will increase the VDS, so we can see that current also increases, and also
see
small
now,
amount of
see now.
depletion region also increases due to the positive charge. But we can see that the if now next what we will do, we'll increase the VGS at the starting.
Here we start to control based on VGS. Here is B, so I will add negative volt.
And we'll keep at a 0 at VDS. So let's say if I will keep VGS
See
at
what
-1
he
volt,
will add more and more reverse voltage. So more and more close channel.
and further if we will increase the VDS, so we can see that current also increases.
See,
and also
again,
smaller.
see the graph here. Excuse me. See the graph here. Focus out about this output. Now here.
Pinch
Your
off
eye here.
voltage. As we can clearly see that in the graph, pinch off voltage after
now there is no
voltage,
VGS. VGS here is
becomes
0.
constant because the channel width become constant. So if now next what we will do, we'll increase the VGS at the starting and we'll keep at
see
the
this
0
one.
at
Focus
VDS.
here.
So let's say if I will keep
See, what about this graph decrease? So VGS for this one start here, VGS 0, then decrease. So here VGS 1, VGS 2, VGS 3 until your eyes for VGS decrease again. And what about the C? Here you have a point. It was here. Now it was here. So we have like this. After a while, let's wait a video and see what will happen for this point. Again, we are talking about here if this decrease, because I have ID here 17 milliampere. Here we have ID, it's 12 milliampere. So what about ID decrease? So if I increase VGS in negative, ID is decrease. It was here 17, now he's 12. See again and focus on this graph because it's important.
VGS at -1 volt, and further if we will increase,
now we will increase this VDS.
Is the VDS, so we can see that current also increases, and also small amount of depletion region also increases due to the positive charge. But we can see that the current becomes constant after a certain section because of depletion, or we can say the channel width remain constant. As we compare the flow of a current with the previous value, we can see that it is becoming constant but at a lesser value as compared to the previous one. We can see in this graph. See, now it is at a 10 milliampere. Previously it was at 20 milliampere when VGS was equal to 0. So again now my with channel width becomes constant, so the current is also becoming constant. Let's say now also
0.
make the VGS at further higher level. We can see that at
See this, start to close, pinch off, where from the drain, starting from a drain, and again VDS 0, there is no current. There's so VDS like like a normal battery. But see this, start here to close. We have a little bit here to pass current, but it doesn't exactly close. So see, start to close. Wait and see about this. This is important.
one point of time, depletion layer is
Here we are. See here, what will happen here? When VGS, this is here on this area. When VGS equal VB equal VB, that's me close channel. I don't have whatever program. Close channel. So when exactly I close the channel at this point, when VGS equal VB. This is the VB here, and this is the VGS. So when VGS equal VB, at this point we can say it's closed channel. Hocam ne zaman current yok? VB, this is for each transit. I will give you an example. When VGS equal VB, see this closed channel. ID is equal 0. So if someone asks you in GFIT where there is no channel when VGS equal VB, so see this from output. Here, cut off region. Repeat again. Focus with me. Today we studied this one because important GFIT. In GFIT, if we have VDS, okay, we have a current. If we don't have VDS, but I have to control. We start from up to down. We start from up to down. See up, this one up here, it was here, 0. Then decrease. See again, current will decrease. Current will be 0 when VGS equal VB. So at this time we can say at a physically channel closed and current now is 0. Got the idea? Or repeat? I want to understand the physical meaning because a little bit hard. Got or repeat? See this? Here when this one equal this one, so we can say when this one equal this one, so we can say there is no current and channel pinch off. Got the idea? Repeat. Okay, let's continue the video.
heading, or we can say touching each other at train section. This will cause the conduction channel, or we can say the channel with to go at zero. So now if we will increase the voltage across VDS, there
There is
will
no
be no
current.
flow of an
Zero.
electron
Closed.
because there is no channel available to go
Ah, channel has closed.
due to the depletion rate. As we can see, this region we can clearly state as a cut-off region where there is no flow of an current even if we'll increase the VDS due to the closing of channel width. At a voltage when there is no flow of an current, that voltage, VGS voltage, is known as pinch off voltage. It is the same voltage at which the current is becoming constant at when we keep at zero and the current becomes constant. So the pinch off voltage is the two voltage we can define. One voltage when the current is becoming zero.
ITS is the first current becomes zero due to the voltage. VG is equal here, for example, zero. And another one, we can define VB in two ways. When the IDS is maximum or constant, or VB when the VG is equal VB, that's mean closed channel. So pinch of voltage, current flow reach the maximum, allowing VG to fully controlled current flow between maximum and zero current.
That is at
But use our definition in our book.
And second pinch of voltage we can say state that when the current is at a maximum level, it becomes saturated. This is the working of junction field effect transistor. Thank you.
Any question for this? Did you understand this now? Did you understand this? Okay. Now, here, if I see the output, I explained on the physical meaning, okay, directly. See here, we have like this. Excuse me, Ben today is not working. I don't know why. Anyway, so see here we have, this is first or VGS, zero, then decrease, at here, see this point? This is VB4 VDS. When VGS equal this for VB, you can say VBF. So focus on this area. When VB for VGS equal VDS at V finish off, so here we can say close channel. And see the current here is zero. So we can define now three regions as you see here. Ohmic region, here area, this area ohmic, and saturation and cutoff. But different meaning that we give to you before in BGT. Clear? Okay. Now let's continue. Here we have definition there about RD, because we said that channel is like resistors. We have definition of RD. I don't need this formula. Just explain that when you have R dynamic based on VGS over VB square. For B channel, like in channel, but with opposite the voltage. How we can know? Take care of this one. Then back up here. If this N, that means this voltage is negative. If it's B, this voltage is positive. N, that's mean negative. I will focus on this voltage. So if N, that's mean negative. If B, that's mean controlling voltage or VGS will be positive. Clear about this? Yes. أداب مين صارك شرطان؟ هذا الشيء كذا كل شيء. So now let's go to the formula. Okay, we have some idea. See this idea. We have here maximum voltage. For example, here if I apply VDS 20 volt, what so so we have for this one we have maximum voltage. This here will happen. We have a breakdown. So breakdown, that means I will pair in my transistor. So you have to work from this area. For example, C to 15. This is guard. Avoid this one. So you have to work operating point from 0 volt to, for example, 15. This is because this is B channel. But for N channel, you have to work for 15 positive or negative based on N or B. After that, stop to avoid to pair in your transistor. So this is like quad. Okay, continue. Symbol for transistor, it's like this. We have like this symbol, and arrow indicates to the N channel. So this is N because N inside, B because B on the side. So for example, this is N. So this is N channel. B here will be on the side. So this is B channel. This is N channel. This is B channel. And VGS, it should be here negative, positive. More correcter than positive, negative. That's correct. If you know, you have to, if you want, this is, I guess, more accuracy. Negative, positive for N and positive, negative for P. Is it clear? A little bit hard today. A little bit hard. Or you can understand it. Okay. I hope. Okay. After that, we have how you with this transistor in the circuit. I will stop here about transfer characters and how we can draw this one. This is for next week. We will finish this one and we'll go to another one called depletion and enhancement. And we talk about this on physical for next week. I know a little bit today is hard, but wallahi, I try to be easy as possible as. So again, inshallah, next week